for joining us for day 2 of our inaugural conference. We'll jump right in, and Seamus is going to tell us about how to be an imprecise impermissivist. And for the non-flossers in the group, what the hell that means.
Cool, thank you. So yeah, I will explain what the terms mean. There's a handout which is available on the website. That's probably the best way to follow along rather than the slides. The slides are just sort of some visual aids. The details, the information is all in the handout. So I should explain that the goal of this talk is in the spirit of the conference to bring together the SIPTA crowd and the philosophers working on imprecise probability. And the way that I'm going to do this is I'm going to be using some formal results that have already been produced by Bert and Jasper and Kike and others, and make use of those results for the purpose of making a philosophical argument. So there's no new formal work here. Okay, I'm just going to be using work that others have done in the goal of providing a philosophical argument. The way this talk is structured is basically I'm going to be giving a kind of rational reconstruction of a debate that people have been having in philosophy. So I'm not going to be recapitulating what people have actually said. What I'm going to be doing is saying, here's how the debate might have gone if everyone was on the same page in terms of like what the formal basis is, and if everyone had had access to the kind of mathematical work that I'm appealing to. Here's how you could have the best version of this debate. And the debate is about whether or not there's a sensible way to be an imprecise impermissivist. I'll explain what that means in a little bit. Okay. The other thing to say is there's a lot of stuff in the slides. There's a sort of information dump there, and I'm not going to go through all of the details, partly because some of the details are less relevant. Some of the details are things that most people will already know. So there's more information in the handout than is necessary, and yet it's also somehow quite sketchy and sloppy. So apologies for that. This, like I said, this is not a mathematical talk, so I've given myself the flexibility to be quite kind of impressionistic about the results. Okay, you just have to trust me that I've done an okay job of like translating what the SIPTA crowd have done into what I'm using it for.
So you're being impressionistic about imprecise impermissivity.
I sure am. Oh, I should have yeah, put that on the thing. So the section headings here match the section headings in the handout. So this is just a way of kind of giving you some pointers to where we are in the talk. So there's three things that we're going to be three themes that come up again and again in the talk. Just to give you a heads up about what they are. The first idea is, so the general question is, how should we manage our epistemic life? How should we rationally constrain our degrees of belief, our credences? One theme, one way people do that is they talk about coherence, right? The idea is that your credences, your rational beliefs should kind of hang together in a certain way, and there are different ways of cashing out exactly what that means. We'll talk about a couple of them later on. Another thing people say is, look, not only should your rational beliefs be, structured in a certain way, but they should facilitate sensible inference. You should be able to learn on the basis of evidence. Your beliefs should change, and they should change in such a way that you come to be in a better epistemic position than you were when you started, right? You should be able to make use of information to make your rational beliefs better, at least in some circumstances. And finally, possibly most controversially, is that in the absence of a reason to treat propositions differently, you ought to treat them the same. Okay, that's normally captured in the idea that your rational degrees of belief ought to satisfy some sort of principle of invariance or symmetry or whatever. And we'll talk about a bunch of different ways of cashing out that idea as well. Okay, so let's talk about that first theme, coherence. Basic idea that I'm working with here is that your rational degrees of belief, your credences, they inform your betting behavior, and a flaw in your betting behavior, something that's wrong with your betting behavior, points to some kind of flaw in the rational beliefs that you use to inform that betting behavior. We're going to kind of go through this fairly quickly because this should be something that's familiar to everyone in the audience here, or almost everyone in the audience here at least. And also, this is something that, Teddy explained, really well yesterday, really clearly yesterday. So I don't really need to go through the details. But the basic idea is, if your betting behavior is such that, if the prices you offer for bets are such that you are a walking, talking arbitrage opportunity, then there's something wrong with your rational degrees of belief, right? I should say, in this context, in the context of Jason's project, there are other ways you can try and cash out what it is for your rational degrees of belief to be structured in the right way. And in fact, you could slot that kind of theory in here. The betting background to coherence in this context doesn't actually do much work. It's this part of the handout is more because it's for an audience that isn't quite so familiar with this kind of betting approach to constraining your rational credences. This is actually quite a sort of good way to introduce the idea of imprecise probabilities, but we don't need to go there. One thing I should say here is that I'm going to be unconventional and possibly slightly annoying in often referring to probabilities, which is the outcome of avoiding being a walking, talking arbitrage opportunity. You do that by having your rational degrees of belief be a probability if you're in the sort of two-sided betting circumstance that people normally talk about. I'm going to refer to that idea rather than talking about your rational degrees of belief being a probability function. I'm going to refer to them as being de Finetti coherent credences. Why? Because I want to emphasize that we don't have a pre-theoretic commitment to probability theory. It's a consequence of committing to a particular way of understanding how to understand coherence. And the reason I want to do that is because later on we're going to see an alternative way of cashing out, or a logically weaker way of cashing out coherence that gives you other consequences. But I want to emphasize that probability theory is sort of a consequence of your approach to betting. So I'm going to skip a lot of the sort of details of section 2 because I hope that's familiar to most people. I just wanted to have an opportunity to put this slide in. I should say as well that your coherence is not just a sort of at a time thing, but if you want to also avoid the possibility that someone can kind of arbitrage you over time, right? Your rational degrees of belief had better change through conditionalization. So I'm kind of folding the idea of conditionalization into being coherent here. Okay. So one answer to the question, how should we run our epistemic lives? What should be the constraints on our rational degrees of belief, is to say that you got to be coherent in that sense, and that's it. And that is a very extreme form of permissivism. It's very permissivist. It allows a lot of different probability functions, allows a lot of different credence functions to be rationally permitted. Okay, it's very flexible, it's very loose. And I call it extreme because I think that view is nuts, right? Why? Because there's lots of bonkers probability functions, basically, particularly in the context where you've got some kind of idea about what it would be to rationally learn. So throughout this talk, I'm going to be mostly talking about learning about outcomes of a coin toss, right? And there's no funny business with the coin. The coin doesn't have memory or anything like that. It's just a coin. You just don't know what the bias is, right? And you want to learn, like, in the sense that you want your probabilities to come to more closely match what the actual chance of the coin toss is, what the actual bias of the coin is, right? So here's a conversation between Alice and Bob. Alice has a coin. She says, I'm going to toss this coin. How confident are you that the next coin is going to land? The next toss is going to land heads. Bob says, it's about 50-50, 0.5 confident the coin is going to land heads. Alice tosses the coin. She says, look, Bob, it's heads. How confident are you now that the next toss is going to land heads? Bob goes, 1%, right? This seems wrong, right? It seems like there's something wrong with Bob's attitude here. Bob's response to the evidence seems inappropriate somehow, but it's not probabilistically incoherent, right? There are probability functions that are such that Bob could conditionalize on the first coins landing heads and get, have his belief move in this way, okay? The probability functions are sort of inappropriate in all sorts of ways, but like, if you let in all of the probability functions, you let in some really nutty ones, okay? I give an example on the handout of these so-called anti-inductive priors, but you can have, other examples of like just making all the evidence propositions, probabilistically independent of the things you want to learn about, right? That's also possible, like a uniform distribution over the state descriptions, for example, right? You don't learn anything in that case. Or, Bob could just have the wrong statistical model in the background, right? Let's imagine that Alice is tossing a coin, n times, and Bob's statistical model is like, drawing, from some urn without replacement. So probably he starts with a high, and you've got, he thinks there's n-1 heads balls and 1 tails balls. So he starts with a really high probability for heads that decreases over time as he sees lots of heads emerging, right? Now, obviously that's inappropriate for what we take the situation to be, but it's probabilistically coherent, right? In the sense that it's a probability function. It's the wrong one, but that's the point. Like this, that extreme permissivism is too extreme. So can we do better? Are there probability functions that give us sort of appropriate learning behavior? And obviously the answer is yes, at least in these kind of simple circumstances, right? At least in the circumstance where we're talking about, pulling marbles out of a bag, tossing a coin or whatever. These are the simple examples where it's perfectly possible to have good, sensible, inductive inference behavior. And the point is, like, I'm focusing on these simple examples. Why? Because if we can't do it here, we're really screwed, right? So let's get it right in the simple cases and then see, and then we can talk about the more complicated cases later. Cool, so how do you learn? This is all remembering a precise probability framework so far. Let's structure our epistemic life in the following way. The probability that the next coin lands head, so H is a sort of bit of a sloppy shorthand for the next coin toss will be head. So if you've got HI for the ith coin toss, and then we have 0 and 1 for it lands heads and it lands tails. So the probability that the next coin toss lands heads, given that we've seen H heads in the first n tosses, so that's just the sum of the first n 0, 1 random variables, right, for heads and tails. So the probability that the next coin toss lands heads, given that we've seen H heads in the first n tosses, should be something of this form. So there's two parameters here, lambda and gamma. We'll explain what they mean in a second. But this is basically it's either exactly or it's something very similar to Carnap's lambda gamma continuum of inductive methods, right? If you set gamma to a half, it's exactly Carnap's one parameter family of inductive methods, I think. But basically, the idea is if n is 0, if you see no coin tosses, right, the first term drops out. The second term is 1 times gamma. So gamma determines your prior for the probability of the coin toss. And then as you learn more, right, this first term becomes important. So if you stare at this for a little while, you can see that as n increases, as n tends to infinity, right, what happens is that term comes to dominate, okay, in the sense that as n tends to infinity, n over lambda plus n tends to 1, right? And lambda over lambda plus n tends to 0. So the first summand comes to dominate, and it comes to dominate. It gets closer and closer to something very close to 1 times h over n. Okay. Now remember, h is the number of heads in n tosses. It should be subscripted. Should I put Sn there or something? But basically, as you toss a coin a bunch of times, the actual frequency of heads in n tosses tends towards the chance of heads, right? So as you learn more and more coin tosses, you are getting closer and closer to believing the right thing. The next coin toss will land heads with probability close to the chance of heads. Okay, cool. So here's some just sort of illustrations of this. Oh, and this you can arrange your probabilities over this state space such that this is actually conditionalization, right? I'm not cheating here. This is basically like the conditional expectation of a beta distribution for an unconventional parameterization of beta distribution. So let's just get a little bit clear on what the parameters are doing. So if you fix lambda and you vary gamma, right, your prior probabilities range, these are different values of gamma. Gamma here is 0, 0.14 or whatever. And then as you gather more evidence, right, these are out, 4 samples from this distribution each time. You tend, you converge and you tend towards the true chance, which I think in this simulation was 0.7. So gamma determines your prior, okay, and then if you fix lambda, they all kind of learn at roughly the same rate, if you like. Go the other way around, fix gamma, vary lambda. What happens is gamma is fixed to 0.3. Every probability has the same prior of 0.3, and they learn at different rates. So they're sort of the bigger lambda is the gray one at the bottom here, the biggest lambda I've shown here, and that learns the least. So it's the most stubborn in a sense. Smaller lambda, the more you change your belief in response to evidence. That's basically the idea. Cool, and pick a lambda, pick a gamma, and you'll learn, right? So this is cool. If you structure your epistemic life in this way, at least for the case of learning about coin tosses, you will learn. You will converge on the truth, right? Eventually. So that's nice. So I should say here that, to get this idea of like, here's some learning behavior, here's some desirable learning behavior going, we have to say something about like, there's a particular kind of structure to the state space in the background that we're learning about, that we're kind of appealing to, right? We're saying we've got, n copies of some, set of outcomes that describe the space, and learning what happens in the ith component of that state space is sort of evidence for, you can use that as evidence for learning about what would happen in other coin tosses, other components of that Cartesian product state space. So this isn't a case of like total ignorance, right? This is a case of some kind of structured ignorance, and that structure is, the idea of structured ignorance is going to be important later on. Okay, so we've introduced the idea of coherence, we've introduced the idea of learning. Let's move on to the idea of invariance. Now, I'll just I'll just say up front that this is the sort of the least convincing part of the talk in the sense that I probably don't buy into this idea of using invariance to do all the things I'm going to do in the talk quite so much. But I think it's sort of an interesting exploration of the space of possibilities, even if it's perhaps an argument I don't fully endorse. So even that, you pick some learning prior, right? So your prior has to be coherent, and at least in cases where it's obvious what sensible inductive inference would be, you have to pick some prior that will learn appropriately. Even that gives you lots of flexibility, right? And two real valued parameters there in the case I gave there. And if you're drawing marbles from a bag, you get more parameters, right? So there's still lots of flexibility to choose what your prior belief should be and how stubborn you should be, how responsive to the evidence you should be. So that's still quite permissive, right? And some people think that the constraints on rationality should not be permissive in that way. They should be that, and these people are people we could call impermissivists in the sense that they think that given a particular sort of situation that you're thinking about, a particular statistical process that you're going to be learning about or whatever, there should be one way to rationally respond to it. There should be one, credence function that's the right one to have, right? There's some sort of uniqueness, right? Your rational credence is sort of maximally constrained to be one specific credence function. So that's what I mean by impermissivist. Okay. But even within that idea of there being a unique probability function or a unique credence function, there's some kind of wiggle room, there's some flexibility. So I like these ideas that Chris Meacham mentioned in a paper from the mid-2010s. One thing you might think is that for a given evidential situation, for a given sort of learning problem or whatever, each agent has some particular credence function that is the one that they ought to have as their credence, right? The other thing you might think is that rationality shouldn't make discriminations among the agents. Whatever rationality requires, it requires the same thing of all agents in a given epistemic situation. Oh, so for each agent, there's only one rational credence. That's the idea of agent uniqueness, right? Meacham calls the idea that rationality should constrain all agents in the same way, permission parity, right? And combine those together and you get the idea that every agent should have the same rational credence, right? As Katrin said yesterday, quantifier order can be tricky. Evidential uniqueness and agent uniqueness are just a quantifier shift away, right? Agent uniqueness says in a given evidential situation, for each agent, there is some rational credence that is the one they have to adopt. And evidential uniqueness says in a given evidential situation, there is a rational credence that for every agent, the agent should adopt that credence. Okay. So even within the sort of impermissivist school, there's some wiggle room about what exactly you're expecting, how unique you're expecting the rational credence to be. Okay, so how do we add further principles? How do we add further constraints on rational credence? One common natural thing to do is to require that your epistemic state or rational beliefs satisfy some kind of invariance principle. And the way this kind of works is you say, let's imagine that you've got your credence for proposition X, your credence for proposition Y, and there's some transformation, some map from your set of possibilities to the set of possibilities that induces something, a transformation on the algebra. And if the transformation maps x to y, then you ought to take the credence in x to be equal to the credence in y. That's what it is to be invariant to that transformation. Okay, and that transformation then induces a transformation on the probability functions, on the credence functions, right? So how strong that principle is, how strong that idea of invariant under a set of transformations is, depends on which transformations you require your rational credence to be invariant under. So the first thing to say is there's no definitely coherent credence, there's no probability function that's invariant under the set of all possible transformations of the state space, right? But that's a very strong thing to require, okay? That's a consequence of a result from Kurt's paper with Kiki Miranda. John Norton has similar ideas. So if we wanted to be that invariant, that would be impossible in a probabilistic setting. But that's very invariant, so that's too much. I think there's a sort of stronger argument against. So this is now an argument against using de Finetti coherence as your requirement for coherence, because we're saying here is a kind of invariance or collection of invariance principles that we want our rational credence to satisfy, that's impossible to satisfy using this kind of notion of coherence, right? So this is basically, I'm just going to be sort of recapitulating with a bit of formal sort of mathematical epicycles, Van Frassen's box factory example. But this, this is basically Bertrand's paradox, right? This is a very old idea in probability. So there's a factory that produces boxes. The boxes are cubes and they have random side lengths. So each box has a different random side length. Okay, side lengths are between 0 and 2 meters. Let L1 be the proposition that the interval 0, 1, and this is the interval 1. L2 is the interval 1, 2. Now, in the absence of any other information about how the box goes about producing its side lengths, we should treat L1 and L2 the same, which means that we should be invariant under the transformation that maps them to each other, right? We have no reason to treat L1 and L2 differently, so we should treat them the same. We should be invariant to the transformation that treats them, that swaps them around. Okay, now there's a box factory that produces cubic boxes where the face area is a random value between 0 and 4 meters squared, okay? And these F1 to F4 are the interval 0 to 1, 1 to 2, and so on. And again, we have no reason to treat these propositions differently, so we should be invariant our credences should be invariant to transformations that permute the indices, right? I haven't put in the whole permutation because there'll be a lot of arrows. Okay, good. Now, plot twist. It's the same factory. Oh no, right? Because face area and side length, are just two ways of describing the same thing, really, right? If the face area is in the range 0 to 1 meters squared, the side length is in the range 0 to 1 meter. And if the side length is in the range 1 to 2 meters, the face area is in the range 1 to 4 meters. Okay. So the problem is that the invariance we want to satisfy with the transformation invariance we want to satisfy among the side length propositions require, if we're in a probabilistic context, that requires that the probability for the next box being in L1 is a half, right? Because they're mutually exclusive and exhaustive, and their probabilities have to be the same. Likewise, the probabilities for each of the FIs has to be a quarter for similar reasons. But the problem is that L1 and F1 are basically the same thing, but they have different probabilities. So that's a problem, right? So there's another kind of invariance that we want to satisfy here. We've got two different languages for describing the same kind of setup, right? And the problem is, if you can identify propositions in the finer grained language that are sort of also expressible in the coarse grained language, right? They should have the same probabilities, right? L1 or F1 is a proposition in this finer grained language that's also a proposition in the coarser grained language. It's L1. So the propositions in the finer grained language that are pre-images of the surjection onto the coarser grained language are propositions that should have the same credence regardless of which language we're using, right? So this kind of language invariance then is a further kind of invariance. It's not a transformation because it's a map between different languages. There's a probability function over the L1s and there's a probability function over the F1s, and there are constraints now connecting these probabilities across the languages. So the upshot here is that there's no probability function, right? There's no definitely coherent credence function that satisfies the transformation invariance we want on the L1 on the L language, the transformation invariance we want on the F language, and this language invariance that maps the two together. Okay, so that's an example, right? We can tighten that up into a more sort of mathematical impossibility, right? Basic idea is that you formalize this idea of sort of coarse graining and what's expressible in the what propositions in the finer grained language corresponds to propositions in the coarser grained language. You can make this into a sort of a constraint across languages that I'm going to call so the mapping I'm calling sort of invariant coarse graining. This is related to our idea from Eric and Jasper's paper with another co-author that they call, well, so yeah, so that's the idea. Like if you've got different languages, right, you can map these across. Now, if your language has that kind of structure that we've been talking about in the background of it being, n copies of some category set, right? And if your coarse graining is induced by some kind of mapping on the category set, right? Which not all maps across languages are, obviously. But if it's induced by some sort of coarse graining, if it's like, you've got your bag of marbles and you've got red, blue, and green, and you go, oh, maybe I should lump together blue and green, right? And then that induces something for the space of n copies of those category sets. If your coarse graining has that structure, and then if you want to be invariant across all possible coarse grainings of that form, so you want to be neutral about how many categories you want to split up the possibilities into, if you like. That's what Kurt and Jasper call prior representation insensitivity in the 2015 paper. Again, I should say I'm sort of translating everything into probabilities and later on sets of probabilities, whereas in Kurt and Jasper's paper, it's all in terms of sets of desirable gambles, which is probably a much more natural way to do things, because this then becomes a bit sort of fiddly. But for the purposes of making things familiar to the philosophical audience, and given the sort of the flexibility I've given myself to be impressionistic, I'm happy to say that this is, close enough for government work, as they say. So, the result then, that the sort of tighter, more formal impossibility is that if you've got a set of credence functions, one for each, collection of category sets, and you want to be language invariant across these, then none of those credence functions are de Finetti coherent. Right. So the idea is, if that's a kind of invariance that you want to satisfy, that strong kind of language invariance is something you want to satisfy, and it's still pretty strong, then you definitely can't use de Finetti coherence. We can talk about whether that's too strong, whether it's crazy strong, but we'll leave that for now. Okay. So what have we done so far? Basically, the conventional standard for coherence, de Finetti coherence, permits, but doesn't require you to have reasonable learning behavior. So if you want to have reasonable learning behavior, that's an additional rational constraint. This de Finetti coherence is incompatible with some strong invariance principles, right? It's definitely incompatible with some invariance principles that are way too strong, right? But arguably, there's also kinds of invariance that we do want to satisfy, like the ones in the box factory example, or like possibly like something like language invariance, which it's also incompatible with. Okay, so let's weaken de Finetti coherence and see whether we can satisfy some stronger invariance principles. Okay, again, gonna skip this fairly quickly because Teddy mentioned it yesterday, and this should be a move that's familiar to everyone in the thing. Basically, your de Finetti coherence kind of starts with the idea that you're doing this two-sided betting. So if you've got a bet that wins you 1 if A is true, right? If it costs you less than your credence in A, you should be willing to buy it. And if it costs you more than your credence in A, you should be willing to sell that bet to somebody else. You should be willing to take the other side of that bet. What happens if we only take the first half of that, right? So you're willing to buy bets that cost you less than your credence, but you're not willing it's not the case that you're willing to sell them for more. That's one-sided betting, and that leads you to what I'm calling Wally coherence, which basically you're Wally coherent if and only if your prices for gambles on propositions are the lower probability of some non-empty set of probabilities. Okay, so I'm going to be sort of using sets of probabilities, lower probabilities, kind of interchangeably. And again, apologies for not getting on the sets of desirable gambles bandwagon, or choice functions, or probability filters. I'm in the interest of trying to keep things somewhat familiar. I'm just going to work with this old and obviously unsatisfying framework. So one thing that there's a wrinkle here, right? That idea of transformation invariance in the precise sense is actually two different principles in the imprecise case that we want to keep separate. So one idea is a strong transformation invariance is just the transformation, the induced transformation on the set of probabilities maps every probability to itself, is strong transformation invariance. And weak transformation invariance is that that transformation on probabilities maps every probability to something in the original set. So the set of transformed probabilities is a subset of the set of probabilities. Okay. So no Wally coherent probability is strongly invariant with respect to all transformations on the set, right? That should be obvious because of what's true of the precise thing, right? But it is possible to be weakly transformation invariant with respect to the set of all transformations on the state space. But the problem is the only way to do that is with the vacuous prior, right? The set of all probability functions on your outcomes, right? So again, this is too much probability, right? So that's my recapitulation of some moves in the debate in philosophy, where people say, look, if you want to be impermissivist and go imprecise, the only way to do that is to end up with the vacuous prior. Okay, that's what people say. That result, the only way to be weakly transformation invariant and Wally coherent is to have the vacuous prior, or Wally transformation invariant across, yeah, weakly transformation invariant with respect to all probability, or with respect to all transformations, is to have the vacuous prior is sort of my explanation of what they might have meant by that kind of argument if they had access to these formal results. Why is that a problem? Well, because the vacuous prior contains all of the bonkers probability functions that we were trying to throw out when we were talking about learning. It includes all the ones that don't learn. It includes all the ones that, you know, are anti-inductive or whatever. So it's bad from a learning perspective, right? So we've managed to be slightly less, we've managed to slightly weaken our coherence requirement, made a, you know, satisfied a much stronger invariance requirement, but at the cost of any kind of satisfying learning behavior, right? And if that were the problem, if that were actually the problem with you know, impermissivism, that would be easy to overcome, because like we don't think the vacuous prior is a good place to go, but we can, you know, find some other kind of prior that maybe some other imprecise prior, some Wally coherent credence that that does better. The problem is that one natural suggestion for what to do almost doesn't work. So let's now look, right, we want to be Wally coherent, right? And we want some kind of satisfying learning behavior, right? Well, let's just take the set of all the learning priors, right? Let's just take the set of all probability functions that take this form for you know, for those parameters, right? Each of them learns. So maybe this has, you know, good, maybe this set of priors has some nice learning behavior itself. It doesn't, right? Why? Well, because if you fix n, right, and let lambda tend to infinity, then this thing gets dominated by the second term. And if, you know, if we didn't constrain gamma, then we're still like, whatever you learn, your you know, your probability is still going to contain every value of gamma that was in your prior. Okay. So that's a problem. Okay. But it's a fairly easy one to solve. Bound lambda. Pick some maximum amount of stubbornness that you want to permit in your set of priors. Okay. Then, so this is again just illustrating this idea of failure to learn, right? The bigger lambda, the closer to just not learning anything you get. Okay. So yeah, just bound lambda, pick some maximum amount of stubbornness that you want to permit, and this is this model is then a special case of the so-called IDM, right? The imprecise Dirichlet model, and an IDM, which is a class of models, one for each collection of category sets, right? For any finite value of lambda, the collection of IDM models, right? One for each set of category sets. They all learn, right? In the sense that lambda's bounded, so you converge on the truth, and they collectively satisfy that language invariance principle that I suggested isn't possible to satisfy in the precise case. So that's the conclusion, right? It's I imagine not very surprising for the SIPTA people, because, you know, IDM is a pretty well explored statistical model, but I think for the philosophy community, it's perhaps you know, given the way that the debate has been going, it's surprising that this is that this turns out to be possible. So let's just wrap up what I've done here. And I think this shows that like there's a perfectly sensible way to be an imprecise impermissivist, right? Right. If we weaken that coherence requirement from Definetti coherence to Wally coherence, we can satisfy invariance principles that it's impossible to satisfy in the precise case. Language invariance, we can get a satisfying model of the box factory, for example. Contra what some people say in the philosophy literature, that doesn't mean, going imprecise in this way, doesn't mean that we have to give up on sensible learning behavior, right? The only question remaining is, well, what value of lambda should we pick, right? Wally says, well, you could probably pick 1 or 2, right? I think Maher, in a different context, ends up arguing for 2 as well. But like, I don't think we have to even have that debate, right? If we want to go for agent uniqueness, right? That lambda parameter, in a sense, is a maximum amount of stubbornness that you allow in your model. It's a measure of sort of epistemic conservativity in a different sense to the one Jason talks about in his forever forthcoming paper. So this is a satisfying model of learning behavior in this simple case in the imprecise setting that satisfies good invariance principles and is suitably flexible to accommodate different attitudes to epistemic risk. And that's the point I want to end on. Thank you for your attention.
Wonderful, thank you, Seamus. Just like yesterday, if you have a question, please put a Q into the chat. And maybe I will kick things off and others think about their questions. So, I mean, I'm happy with the idea.
Good, jump on.
But I do wonder whether what the rules of the game are for deciding what kinds of invariance principles are reasonable to expect. I mean, it seems to me like, look, whether you want your model to satisfy an invariance principle is not like an a priori. Invariance principles encode empirical information that might be appropriate for a given inference problem.
I mean, one invariance principle is exchangeability. I didn't talk about that, but that obviously suggests something about the kind of what you take to be the data generating process.
Yeah.
Sure. Yeah.
I mean, and like in Bertrand's paradox, there are different ways you can set up Bertrand's paradox where different invariance principles seem plausible.
And if you describe how the box factory works, right? They pick a number uniformly from 0, 1, or from 0 to 2, and use that to determine side length. Then being uniform over side length is the right thing to do, and that gives you non-uniform distributions over phase area.
Yeah, I mean, and well, I mean, I guess the like broad background point is, given that different invariance principles capture different empirical information that you might have about a given setup, it doesn't seem problematic that you can't satisfy all invariance principles. I mean, those just might amount to inconsistent information. So we need some sort of way to sort out which principles are consistent. I mean, and maybe, I mean, I'm not a precise Bayesian, obviously, but I can imagine somebody saying, well, look, this is just a litmus test for when you've got consistent empirical information.
So one thing I skipped over in the interest of time was that you might want to make a distinction between wanting to satisfy an invariance principle because you have some kind of positive reason to think that you ought to treat those two things the same, like L1 and F1 in the box factory case. You should treat them the same because that's the same thing. That's the same proposition. Whereas why should you treat L1 and L2 the same? right? That's more just like a default position. Well, you don't know, you don't have any reason to treat them differently, right? And so you absolutely should satisfy the things you have, some sort of explicit reason to think you should treat the same. And then the question is, well, how many of those default invariances, how many of those default assumptions can we satisfy? Not all of them, obviously. Which ones are appropriate? Well, that depends on what you know about the situation, right? And this was something else that I skipped over in the interest of time. You want to make the distinction between the case of sort of structured ignorance, right, where you're like, okay, we're tossing a coin, we're pulling marbles out of a bag. That gives you a bunch of information, even if you know nothing about the distribution of marbles. You know the state space is structured in a certain way, right? You know that information about the ith component of the state space is something you can use as evidence for what the j component of the state space is going to be, right? If you're in a case of like total ignorance where you know literally nothing, I just give you like a set and an algebra over that set and say, how are you going to make inferences on that set? Like, there's nothing sensible you can say there. And there, in fact, like, maybe if you want to satisfy all of the default invariances, right, you end up with the vacuous prior, but that's okay, because like, why should you be expected to be able to have any kind of sensible learning behavior in that kind of situation where you have nothing to go on? Like, you need some purchase to rule out some of those default invariances almost, right?
I'm picturing like this episode of The Simpsons where Homer's stuck in quicksand, and he's like, and now I'm gonna pull my feet out with my hands, and I'm gonna pull my hands out with my like, you need some purchase to pull yourself out.
Exactly. Exactly.
Okay. It looks like we have a few more questions now, so maybe Kirk next.
Yes, I have a question and first a comment. I remember being in a conference 3 years ago, you mentioned, where I think the first part of your argument, the impossibility argument, was mentioned, and I remember thinking at that point, like, somebody ought to explain at some point that it's more subtle than that. And I never got round to it, but I'm very happy that you took the effort to explaining that it is indeed more subtle than that. And now the second thing is related to your comment. I think what we do in the paper that is mentioned, that humongous paper.
95 pages.
95 pages. We try to do two things, I think, and the one thing is that you can have I think we call it an inference system. I'm not sure, but so that is coherent in the sense of updating coherence, updating coherence, but it's also invariant under certain transformations. And what we show is that you can have conservative inference under those invariance principles. So you just impose an invariance principle, and then you have a whole inference system, and you can do conservative inference with that too. So in the sense of that, logic is conservative inference. And so you can impose as many as you want, and some will be incompatible and lead to short loss and inconsistency, but other will be compatible, and there will be a conservative inference system under that. So that is one aspect, and I think that answers your question to some extent. The other thing is that why it took so long is that we started out with a number of principles for which we initially thought that they would lead to a unique family system, namely the IBM family. Turned out not to be true, but still got us to our attempt produced this happy side effect of producing the idea of conservative inference in the invariance.
So that's something that again, I sort of mentioned in the handout but glossed over in the talk in the interest of time. But you can use these invariance principles to pick out in the precise case. You can use you pick just the right invariance principles, and that uniquely determines the family of learning priors that I'm talking about, right? And you add a further principle, and that constrains the gamma parameter to be half or 1 over n for picking marbles from a box. And yeah, and I was sort of slightly disappointed that you didn't get the same result in the imprecise case. Although that given an additional principle, everything coincides for the case of one-shot inference, right? But yeah, so you can use these principles. I mean, the invariance principles are kind of super interesting. You can use them for a bunch of different things, right? In one case, you can, if you want your system of inference to be language invariant over a suitably rich collection of possible state spaces, then that forces update to be conditionalization, even if you don't require that, which is a super cool and slightly weird result. So we'll talk about it later. It's a bit complicated, but yeah. So you can use these invariance principles for all sorts of things. And they're a lot of fun, and we should think about them some more.
Yes, I have perhaps a less important question, but a more detailed question about your figure. I think it's in the section about how to learn. Yeah, actually for both of the things, but let's look at the second one.
Yeah.
What does the abscess mean? Does it mean the conditioning events? Or?
The axis is, yeah. So the leftmost point is the prior. The next point is what those probability functions become after they've learned 4 heads, right? And then you add another one. Oh yeah, 1 head and 3 tails.
Right.
So it's cumulative, right?
It's cumulative.
Yeah,
right.
yeah,
Thanks. I didn't understand. Great.
Yeah.
Okay.
Why it would be convergence.
Yeah. Otherwise,
yeah.
No, exactly. It would be straight.
Yeah.
No, yeah. Sorry, that should be cumulative. So you could put it, yeah, as like 4 heads, 0 tails, 5 heads, 3 tails. You could add them together, and that would be like the total evidence. Yeah, that would be another way of framing it. Yeah.
Great. Thanks. That was, yeah.
Yeah, a comment and a question. As far as the comment goes, so there's this result. If you want to satisfy all invariance things, then you should just become vacuous, and then so
yeah.
What's the point? But then I wanted to clarify that invariance where, because there's 2 things going on. On the one hand, all the examples you're giving, like the factorial, so there's a series of there's a repetition of things going on, right?
Yes.
And you can, on one hand, think about being invariant about your information about one of these things, and on the other hand, you can say like, oh, if I also do like transformations over time and then switch around stuff there, then all these kind of transformation also like should not change anything.
Yeah.
And these are 2, and so this result, if you want to satisfy all invariance, you must be vacuous, is true, but the whole point, I think, which is why the IDM also doesn't satisfy all invariance, but it does satisfy it on like a one instance at a time, and that's why it is vacuous in the IDM. If you have no data, it says no, I'm vacuous. And then after you've learned, you don't need to be invariant anymore because there's some symmetry there because you have data. So I think do we want invariance in this global sense or just locally? And I think I find that an important point that kind of may lead to confusion.
Definitely, yeah. And this sort of goes back to this idea of like what your starting position is if you're in this case of like total ignorance where you're given an unstructured set and say learn on that, right? What are you expected to do, right? Whereas if you have a state space that has some structure that is like n copies of the category set or whatever, and it's not just like the cardinality is 2 to the n, like you take there to be some kind of structure encoded in those n-fold collections, then of course satisfying all invariances, you know, just swapping everything over is nuts, right? Because you know there's some structure there. So that's the thing. Like once you're in that state of having, you know, a state space that has some structure that you think is relevant to your to how you're going to make your inductive inferences, then you shouldn't satisfy all of the invariances, right? Because some of those transformations do all kinds of weird things, like they swap, you know, oh, I get a green outcome in draw 3 with, you know, you swap that with I get a blue outcome in go 5 or whatever. I'm like, what the hell are you doing? Like that doesn't make any sense. Why would we want to be invariant across those? But in the case of like total ignorance, where you know, unstructured ignorance, where you just get this state space, like, yeah, maybe, you know, for any two propositions, like, you should treat them the same because you know literally nothing. But in that case, like, why expect there to be any kind of sensible learning? The vacuous prior is appropriate then, and you shouldn't be able to learn, right? Yeah. So, but that's really, you know, those ideas kind of go together, right? As soon as it's the case that you don't think you should satisfy all of the invariances, it's because there's some structure that you want to kind of preserve, i.e. invariances you don't want to satisfy, right? And that's the case where, well, now, like, you know, you can exploit that structure to scaffold on some, you know, contentful inductive inference. Yeah,
exactly.
No, yeah. So that, but I take the point that maybe it wasn't. I didn't sort of make that idea clear enough that like the you know, transformation invariance with respect to all transformations is like a lot.
It's just like the fact that on a one experiment at a time basis, it is possible to satisfy them all.
Definitely.
All invariance principles, all the fine graining, you can satisfy all of that.
Yeah.
Like one thing
one
at a time and learn.
Yes.
And so I think that's a very strong feature of, for example, the IM that you can do. And okay, that there's a relation between the experiments. Yeah, you kind of have to build that in to learn. Seems self-evident.
Yeah, of course.
If there's no relation, then there's no learning. I mean,
exactly.
Some influence to go in.
Yeah.
I also have the question kind of
sure.
against my own. How do you say that in English? My own shop, or which is you kind of want to have coherence, or at least like in this story you do, and you want to have coherence over time.
Yeah.
There's one thing, coherence is about not being able somebody to combine bets and screw you over. But it's quite controversial why you would want to have that over time. If I now have beliefs about something, and then next year, should I really kind of like be like the gambles I'm offering there or willing to accept? Should I kind of take into account what last year I also have these other gambles and I should not forget about those, should be kind of remain compatible forever, because otherwise those will be on the table. They will remain on the table forever and ever. So the remainder of my life, whatever I want to gamble is dependent on this one thing I said in the beginning. It's kind of controversial. I don't know whether you have kind of a stance there, or
better to just avoid betting to keep your options open for later on, right? Yeah, no, I
put the past gambles like they are
just,
no longer offered, like
just commit to not committing the sunk cost fallacy. So I'm not particularly strongly committed to the idea that you should be kind of jointly coherent across time in that way. It was just a kind of, look, I'm introducing, you know, coherence. It's a cheap and easy way to say we should update by conditionalization. I don't want to like get into thinking about, well, what might you do instead of conditionalization? And in fact, like I said, you know, as you saw, like the stuff on coherence and betting was really just used to introduce like probabilities and the lower probabilities. And I could do the same talk, just get rid of that and just say, here's the model of belief, probability, conditionalization. Here's another model of belief, you know, of which that's a special case, lower probabilities or whatever. and you wouldn't really lose anything in terms of the rest of the argument, right? So yeah, I mean, I agree. Like that's a controversial point, but it was something I did just just to get conditionalization on the table without having to just stipulate it.
Okay, Catherine and Teddy, are either of these a follow-up or are they both new lines of questioning?
Yeah.
Teddy, is yours new?
You go first. No, Teddy can go first. Fine.
Okay. Well,
We can talk over coffee or whatever.
We'll let Teddy go first. We still got 10 minutes, so we can fit both in 8 minutes. Go ahead, Teddy.
Okay, thank you. I'd like to ask Seamus a bit about what the formal requirements on learning are. What does it mean to say that your procedure learns? Do you mean at each stage something is going on or only asymptotically?
Good, thanks. Yeah, I mean, for the purposes of this talk, so I don't have a sort of general idea, a general formal sense of what it is to learn. In the context of, you know, learning about coin tosses or drawing marbles from a bag, learning is going to be something like, you know, converging on the actual, on the chances, on the you know, tending towards the parameters in the underlying model, you know, that the statistical model that you're drawing from, right? So it would be tending towards the actual parameter in your you know, Bernoulli trials or whatever. It's somewhat loose, but it's supposed to be a kind of asymptotic. It's not supposed to be something that's happening at each stage, I think.
So I mean, now we're into delicacies about quantifier order, to use a theme you've already mentioned. Because if I use, say, the set of beta priors, and I think of this as a community of precise Bayesians, and we're thinking of it that way, each one learns, but the community does not learn.
Well, if you bound, I mean, if you have,
if I take a set of all beta priors, then each
that doesn't
one
learn.
learns and the community does not learn.
That's
If I bound them, it depends on the kind of learning in terms of rate of convergence, or whether it's uniform convergence and so on, will depend on the nature of the, it's a topological question. It has to do with the nature of the extreme points of the convex set that represents the joint distributions. So, I mean, what I'm suggesting is that this word learning is papering over many different concepts that need to be teased out. And I think you want to be careful about using one word to describe different aspects of learning.
Right. Yeah. I mean, I think that's probably true. I mean, I think that I can at least say this: if I bound the lambda parameter, right? So every you know, probability in the set has lambda less than some value, then the lower probability of that set of probabilities will converge almost surely to the chance of heads.
So, I mean, this is an issue I think that's discussed in robust statistics. The simplest way I can put it is if the set is encompassed in a convex set with finitely many extreme points, and the extreme points are mutually absolutely continuous, then you'll get uniform convergence. But we're into details about whether the convex set has finitely many extreme points, more than finitely many extreme points. That's what's going to be the question.
I don't think that's true. I mean, I don't think the convergence here relies on your your paper that sort of generalizes the Blackwell and Dubin's result, right? Because you have a closed form solution for the lower probability for a set of beta priors with, lambda bounded away from infinity, right? And that closed form expression converges to the actual frequency as n grows.
But it won't converge in uniform topology in the sense that if you ask at any point what the maximum difference is between opinions, which is the Blackwell-Dubin's merging, you will not get that sense of learning.
Oh, right. Yes. Okay. Right. I see. No, I was just thinking of like it converges.
That's why I'm stop now. That's why I'm saying I think this word learning is papering over too many different issues, and you need to tease them out, just like you're trying to tease out different senses of invariance. You have to tease out different aspects of learning.
Yes. Okay. That's I take the point. Yeah. Thank you. That's I hadn't thought of that. Yeah.
Great. Thank you.
Okay, so we've got these weak and strong transformation invariants where we have transformation space. And I'm just trying to understand the language invariance and how it's related to that. Like, I was expecting what to see was that, oh, we now not need to do it not for all transformations, but just for a certain class of the ones that fit. Is that what language invariance is doing? Is it doing something else?
So the language invariance, what I'm calling language invariance, and transformation invariance are different things. So transformation invariance is about functions from a state space into itself and being invariant.
That's the transformation.
That's the transformation invariance.
Yeah.
And then language invariance is it's a constraint on two probability functions, one for each state space, given a map between the state space. Between two languages, if you like.
Like the language of edges and the language of volumes.
Exactly. Yeah. So they're different in that sense. There's a relationship, right, in the sense that if you take the two spaces in language invariance to be the same space, right, and do language invariance for those kind of maps, that's going to constrain you. But I haven't explored whether all of the, I haven't explored exactly what you get out of just thinking about language invariances on the same language. Jasper and I had a bit of a conversation about some of these ideas. There's a slight wrinkle in doing it straightforwardly, in the sense that, if I get this right, if you just think about the language invariances onto itself, you get weak invariance, but you have to get that. It's not a subset relation; it's an equality. I think it's vague now, and I wasn't quite framing it in the same way as I do now. So that's something to explore. Yeah.
Okay. Well, that brings us to time. So let's thank Seamus.